Graphs of polynomial functions. In the previous section, we explored the short-run behavior of quadratics, a special case of polynomials. In this section, we will explore the short-run behavior of polynomials in general. Short-run behavior, intercepts. As with any function, the vertical intercept can be found by evaluating the function at an input of 0. Since this is evaluation, it is relatively easy to do it for a polynomial of any degree. To find horizontal intercepts, we need to solve for when the output will be 0. For general polynomials, this can be a challenging prospect. While quadratics can be solved using the relatively simple quadratic formula, the corresponding formulas for cubic and fourth-degree polynomials are not simple enough to remember, and formulas do not exist for general higher-degree polynomials. Consequently, we will limit ourselves to 3 cases. 1. The polynomial can be factored using known methods, greatest common factor and trinomial factoring. 2. The polynomial is given in factored form. 3. Technology is used to determine the intercepts. Other techniques for finding the intercepts of general polynomials will be explored in the next section. Example 1. Find the horizontal intercepts of f of x equals x to the 6th power minus 3x to the 4th power plus 2x squared. We can attempt to factor this polynomial to find solutions for f of x equals 0. Factoring out the greatest common factor, factoring the inside as a quadratic in x squared, then break apart to find solutions. X squared equals 0, x equals 0, or x squared minus 1 equals 0, x squared equals 1, x equals plus or minus 1, or x squared minus 2 equals 0, x squared equals 2, x equals plus or minus the square root of 2. This gives us 5 horizontal intercepts. Example 2. Find the vertical and horizontal intercepts of g of t equals t minus 2 to the squared multiplied by 2t plus 3. The vertical intercept can be found by evaluating g of 0. G of 0 equals 0 minus 2 squared multiplied by 2 times 0 plus 3 equals 12. The horizontal intercepts can be found by solving g of t equals 0. Since this is already factored, we can break it apart. T minus 2 squared equals 0, t minus 2 equals 0, t equals 2, or 2t plus 3 equals 0, t equals negative 3 halves. We can always check our answers are reasonable by graphing the polynomial. Example 3. Find the horizontal intercepts of h of t equals t cubed plus 4t squared plus t minus 6. Since this polynomial is not in factored form, has no common factors, and does not appear to be factorable using techniques we know, we can turn to technology to find the intercepts. Graphing this function, it appears there are horizontal intercepts at t equals negative 3, negative 2, and 1. We could check these are correct by plugging in these values for t and verifying that h of negative 3 equals h of negative 2 equals h of 1 equals 0. Try it now. Find the vertical and horizontal intercepts of the function f of t equals t to the 4th power minus 4t squared. Graphical behavior at intercepts. If we graph the function f of x equals x plus 3 multiplied by x minus 2 squared multiplied by x plus 1 cubed, notice that the behavior at each of the horizontal intercepts is different. At the horizontal intercept x equals negative 3, coming from the x plus 3 factor of the polynomial, the graph passes directly through the horizontal intercept. The factor x plus 3 is linear, has a power of 1, so the behavior near the intercept is like that of a line. It passes directly through the intercept. We call this a single zero, since the zero corresponds to a single factor of the function. At the horizontal intercept x equals 2, coming from the x minus 2 squared factor of the polynomial, the graph touches the axis at the intercept and changes direction. The factor is quadratic, degree 2, so the behavior near the intercept is like that of a quadratic. It bounces off the horizontal axis at the intercept. Since x minus 2 squared equals x minus 2 multiplied by x minus 2, the factor is repeated twice, so we call this a double zero. We could also say the zero has a multiplicity of 2. At the horizontal intercept, x equals 1, coming from the x plus 1 to the third factor of the polynomial, the graph passes through the axis at the intercept, but flattens out a bit first. This factor is cubic, degree 3, so the behavior near the intercept is like that of a cubic. With the same S-type shape near the intercept that the toolkit x cubed has. We call this a triple zero. We could also say the zero has multiplicity 3. By utilizing these behaviors, we can sketch a reasonable graph of a factored polynomial function without needing technology. Graphical behavior of polynomials at horizontal intercepts. If a polynomial contains a factor of the form x minus h to the p power, the behavior near the horizontal intercept h is determined by the power on the factor. P equals 1, single zero multiplicity 1, p equals 2, double zero multiplicity 2, p equals 3, triple zero multiplicity 3. For higher even powers, 4, 6, 8, etc., the graph will still bounce off the horizontal axis, but the graph will appear flatter with each increasing even power as it approaches and leaves the axis. For higher odd powers, 5, 7, 9, etc., the graph will still pass through the horizontal axis, but the graph will appear flatter with each increasing odd power as it approaches and leaves the axis. Example 4. Sketch a graph of f of x equals negative multiplied by x plus 3 squared multiplied by x minus 5. This graph has two horizontal intercepts. At x equals negative 3, the factor is squared, indicating the graph will bounce at this horizontal intercept. At x equals 5, the factor is not squared, indicating the graph will pass through the axis at this intercept. Additionally, we can see the leading term. If this polynomial were multiplied out, would be negative 2x cubed. So the long-run behavior is that of a vertically reflected cubic, with the outputs decreasing as the inputs get large positive, and the inputs increasing as the inputs get large negative. To sketch this, we consider the following. As x approaches negative infinity, the function f of x approaches infinity. So we know the graph starts in the second quadrant and is decreasing toward the horizontal axis. At negative 3, 0, the graph bounces off the horizontal axis, and so the function must start increasing. At 0, 90, the graph crosses the vertical axis at the vertical intercept. Somewhere after this point, the graph must turn back down or start decreasing toward the horizontal axis since the graph passes through the next intercept at 5, 0. As x approaches infinity, the function f of x approaches negative infinity, so we know the graph continues to decrease and we can stop drawing the graph in the fourth quadrant. Using technology, we can verify the shape of the graph. Try it now. Given the function g of x equals x cubed minus x squared minus 6x, use the methods that we have learned so far to find the vertical and horizontal intercepts. Determine where the function is negative and positive. Describe the long-run behavior and sketch the graph without technology.